in there with them. Okay, everybody, thanks for showing up today and braving the kind of unseasonable cool for the spring. It is my pleasure to introduce Dr. Allison, who is going to talk to us a bit about math and art and maybe some computer science even.
Can you all hear me? Good. Okay. My talk has, well, 8 parts, but yeah, I'll go through them. Number one, the first one is number theory. Now, you may not feel that number theory will give you any art. Here, I just start with a division plot. So the division plot is pretty simple. You probably did it in your elementary school. Say I just list all the numbers from 1 to 13, and then I try to find out all the divisors of all these integers. So say 6, you get 1, 2, 3, 6, and then I just line up the integers. line up the divisor. This is the row for 2, 3, 4. Then you see a pattern like this. Okay, now this is not that interesting, and then we can move on to look at another one, that is the divisor plot around 100. So that to produce this plot, we use the same mechanism. And now when I look around 100, 100 has a factor 10, that is 10 times 10. We can also observe that for 99, 9 times 11 is 99. And then here, 96, it is 8 times 12. And then 91 is 7 times 13. And it seems that there is a parabola here. Somehow I can fit a curve. And actually, if you think carefully and do some math, like a plus b times a minus b is a squared minus b squared. That exactly gives you 99. And then if you do a little bit more tricks, then you will find out, oh, yeah, actually, they are always there. You predict that they will be there. And if you do a little bit more work, you should find that this is fully a parabola. By parabola, I mean you can fit a quadratic equations, and that will be a y squared. Okay, then you may think about, hey, it seems that there is some pattern in the divisor plot. Is there more? Okay, this is the divisor plot around 1 billion. So this is the 1 million plot, and then this is the square root of 1 million. And then you can see like a pattern like a star. All these dots, they are the divisor. And other than this circle, you can also see other parabola. It all just occurred nicely. Some people also play with the divisor plot. Okay, for the plate cover, I just give you a brief idea of what we are doing. We are working on the divisor plot just to get some patterns. And actually, we can get some songs from that. So, oh, no, not even example. Before the song, let's check another one. It is around the 12 factorials. Oh, that is there. 12 factorials. We know that 12 have a lot of factors. That is 2, 3, 4, 5, 6. No, 2, 3, 4, 4, 2, 3, 4, 6. And a few more. So the 12 factorial, it has a lot of factors, and the divisor plot, you just get many divisors, and then there are also other patterns. That is a straight line, all star, all center from the 12 factorials. Okay, now other than this pattern, we can also get a song from that. Let's see. Okay, to understand this kind of song, we have to start from the beginning. The beginning is pretty simple. Like here, I have a highlight 1. It means that when I find a number who has a divisor 1, I will give it a star. Oh. Okay, now that is what you expect because every number, one is the divisor, it's a divisor of each number. So when you run through all those numbers, one will keep on occur. So you will just hear the same sound repeatedly. If I change a little bit, say consider 1 and 2, then you should expect in every bit you will hear 1, and in every 2 bits you will hear 2, right? That is what should be. And okay, now we can use this kind of way to generate different kind of music. This one is using some factors of 12, yeah, multiples of 2 and 3 and 4, and some multiple of 5, and then generate another kind of music. So it means that you will hear the same sound again. And that will repeat it. Some sounds will repeat it more frequently, some will not. But at the end, it will generate a piece of sound or melody, if you like. That tells you something about the numbers. Okay. Just guess what happens if I get a prime. If I list all the prime, or well, just try to, instead of doing some numbers like this, I can try prime, or maybe prime no. Oh, let's see what it is. Okay, it has the numbers, prime number from 11 to 37, and this is the now, the special features is that it has no divisor other than itself and 1. So if I highlight like the from 11 to 37, this will not repeat until 11 times 13 times, keep on multiplying all the times to get a very large number. It won't repeat so quickly because every 11 bits, you only hear one noise, one sound for the 11. And then every 13 bits, you will hear the 13. Do you like this? Well, you can. There are quite a bit of that in this website. Other than this one, so let me go on. It will still be about number theory. Next time we talk about kind of how to partition certain polygons to make some pattern. This kind of timing, this one is called integer factorization. It is based on the theorem that every integer is greater than 1 can be represented uniquely as the order of prime number, and of course up to the order of factors. For example, 455, I can write it as a product like this, and then I call them P1, P2, P3 for this prime. Then in order to get a tiling that with 455 tiles, I will start with a regular polygon with P1 size. So say here it will be a pentagon of 5 sides. And then for each piece, I further partition it into 7 tiles. Because here is a 7, so I would do it in 7 pieces. And I would do it for each of these subtypes. And then at the end, for each type, I further divide it into 30 pieces. And of course, at the end, we will get 455. This kind of tiling, you can have different variations. This is the one that I showed you. And then these are some others that contain the same number of types, but use different metrics. I'm not sure whether you know about metrics. We have different ways to talk about distance, and once you change the metrics, you will change the pattern as well. Basically, it just control on the previous slide on how you do this partition. Like, how come I can group it like this seven pieces? Can I change it in other way? The metric will determine how you partition the type, and then at the end, it will give you different patterns. So for this number, we get 4 different way of finding, depend on the matches. Here there are some others. This is 5 times, and then this is 25, and then 5 to the power 3. It uses a approach that well, it has explained in a paper called modular form approach, and then it somehow group the 4th one together, and then if you keep increasing the power, at the end you will end up pictures like this. This one have 5 to the 5 times. By the way, when I present all these, they come from papers. This is a very new paper on a very recent paper on time. Okay, and let's see. Oh yeah, here is a video showing how to do this kind of this is a type for here in the bottom and then it needs the factor here. Whenever you have a bracket, you can see a kind of circle. All these are generated by computer. You just program it, ask it to produce it all the time, and then the coloring we have. There is one screen. You adopt it, and then it will apply the color all the time, and then it will generate all these numbers. You can also think that because each number have a unique factorization, its pictures. After you choose the matrix, each picture represents one number. That is unique. If I give you the number, you know, I mean, if I give you a picture, you know the number. If you give me a number that corresponds exactly one picture. Now here we are in 2003, and I have given here I showed you the 2023 type. It looks pretty, and then we can also change it a little bit. This one is also use the same method, but you choose the number of times slightly. Choose one that is a factor of 4. So when you first start with, instead of a pentagon, you start with a square, and then you will generate a lot of types, and of course you can choose to color it in whatever the way that you like. So at the end, you may end up in some pictures like that. People who do like to do something like this, they just integrate the tilings of the pictures. Next, I will talk about the distorted world. This distorted world, if you use mathematics, then it will be non-Euclidean job. The first one is the anamorphic art. It occurred long time ago. People know how to do this. Like if you get a curve, that is reflexive. When you look for it, you can see the pattern on the plane. So well, the pattern on the plane is a little bit different on the cup. Otherwise, after reflection, it won't show it. For example, this one. If you like to see this picture from the reflection, then when you draw it, you have to somehow treat your image. Otherwise, you can't get it. And here is the one that I like a lot. This is the person. If you just look at this graph, you may not see that is the person. But you have to with this cylinder, reflective cylinder to see it. So this person, it has the hair. That is the hair. And then these are his eyes. And then this is the nose here. And then this is his eye. Can you get it? Okay, well then you may wonder, hey, I'm just a teacher. How come I can do this? Well, this is drawn by artists, but surely the artist knows some geometry. What kind of math is needed in order to draw such a picture? Well, then we may need to recall what we have learned in linear algebra. We have learned linear transformation, so that means if you get a grid, like in the XY plane, we can do different transformation, rotation, reflection, scaling, then the grid will change. And the answer we have is a non-linear one. It is not very different from the linear one. If you learn the linear one, you should be able to figure out, oh, well, I get some equations, I can also do that. And so if you get a grid, on the XY plane, a nonlinear transformation will just map it into something nonlinear. I think if you in the calculus course, you will also learn something like this. So the idea is that you look from here, and then it reflects from the cylinder to the paper, from the paper to the cylinder. And so if you get a grid, well, if you get a grid on the cylinder, if you wish to see a grid from the cylinder, then you should have a grid like that. So say if you think about, I wish to draw a man's face here, then you try to figure out how the man's face could be, where the eye is located, and at the end you fill in the details with more hard work, and you can get a picture. And of course, you can also use computer to do that. Okay, that is another kind of projection. That one you will be more familiar with. And let me show you a video on that. Video. So it starts with a sphere with some pattern, and then you put some light on the pole or on the top of the sphere, and then try to generate a pattern. You can also observe, like in order to draw the hexagon that is of the same shape, on the top, the hexagon has to be smaller. Right here is smaller, and those are bigger. And I also make some here. I see the line. You can have a look, and of course you need some light. So also can do that. If you wish to try, you can have the light on, and then probably you need to find somewhere that is a little bit darker. Then you will also see the same pattern, and also get a few more. They will generate different patterns when you light them. So we find it dark. By the way, all those are printed from the 3D printer at the university. So you can also print your, if you like, for whatever you like to get projected, you can breathe in. Okay, so that is the one that I'm passing through. The square one, and then another one that is circle. Now, what I just did, or what the videos demonstrate, is the stereographic projection. From the projection, the grid on the sphere look like this, and then at the end it gives you a very nice rectangular or square grid on the plane. We can observe that, like, how the parallel lines on the plane appear on the sphere. Like, here we get the parallel line, the horizontal one and the vertical one. But before we get projected, there are actually some circle. And they are the circle actually passing through the pole. If you fill in the top here, then that one, like the North Pole, you get all those circles passing through the North Pole. After projection, they will become lines, and they will become parallel lines. And you can also check like how the right angle on the plane appear on the sphere. Like here, these are the right angle, and if you get the models, you can check the angles here to see whether it is the right angle, and I don't think it would be. Also, you can check how does one unit length on the plane will appear on the sphere. So here, only this is one unit, this is another unit, and then when it appear on the sphere, so it will have different length. When it goes further away, then it will become smaller. Otherwise, when you project it, we won't get it done. Okay, this is the stereographic projection. You can use it to project anything that you like. This one is my example. I also have passing through it. We actually live in a place that with distorted angle, distorted length, and no parallel line. We know this kind of world very well. You may think that, okay, well, this kind of world looks very unfamiliarized, but we know some kind of world very well. Even the bird knows, because like when the bird fly, when it looks through a building, the building should look like this, right? That is how a bird looks. Well, if you are an everything, you check the building look like this, and you can tell, even from this picture, you can tell, oh, this is the right angle, this is the right angle, this is the right angle, even they are not right angle on the screen. And also you can tell the length, this is a unit length, this is a unit length. This one is a little bit longer than that one, but you can still tell, oh yeah, it is the same length. We visualize the three-dimensional space, that is the real world that we live in. Very often in a two-dimensional plane, we call it projected plane in math, but if you don't use math language to talk about it, it's just something that we can like use the camera, use the photo to capture it. So we know some space like this, some space that with kind of funny parallel line, funny angle, funny length, but we know that. With this kind of this one is called perspective. When we project the three-dimensional space to the two-dimensional space. Mathematicians truly know about it. These pictures are from a mathematician. He works on topology. He was very famous. His work in topology is very famous, and also his artwork is famous as well. And here he adopts the perspective in his artwork. And I also showed you another one. This is not a mathematician, he is an artist, and he also used perspective. This is not well, this is just a plane, but he can somehow tie it so that when you look at it, you feel that that is something that comes out. And here also have a gallery for that. You can have a comparison of mathematician work and artist work. They use the same techniques though. So what we have gone through is what we call the spherical geometry. It is a little bit different from the geometry, the flat one or the Euclidean one. That's your in a case like if you get a triangle, then the sum of angles will be 180 degrees, and then also you get the parallel lines. On a sphere, all parallel lines they pass through the pole, and then a triangle will have the sum of angle greater than 180. And there is another one, we call it hyperbolic. The sum of angle will be a little bit smaller, and then any parallel line at the end will diverge. They will never meet, and then also diverge. Here are some hyperbolic tiling. So on the top here, it is the flat one. The flat one, we know it very well. We use the hexagon, and we know that the hexagon can package together. That is 3 hexagon meets in a vertex. So 3 hexagon, put it together, then you get the tiling. This is in the flat surface. And in the hyperbolic world, we can do something similar, but not in a hexagon. We can have a full 7-size polygon. So here, 1, 2, 3, 4, 5, 6, 7. All these are 7-size polygon, and then they will tile. Each three polygons will meet in a vertex. So that is 1, 2, 3, meet at 1, and then 1, 2, 3, meet at 1. In the hyperbolic world, anything that is far away will get smaller. That is what I just said, it gets smaller. So it will, the way to tie it will be a little bit different from what we have in the normal case, on the flat case. And of course, you can do a little bit more work to change it to a hyperbolic part like this. This one is still the same. It is still a 7-size polygon. You can check 1, 2, 3, 4, 5, 6, 7. Another one also 5 or 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. And then all of them has 7 sides, and 3 of them will pack together. We'll share one vertex. There is also animation for that. Okay. Now that is the one that I have. 7 polygon, 7 sides, and then 3 of them share one vertex. You can use this one to check, like, if I reduce the size of polygon, will it work? Well, you see that it doesn't change, right? I change it to 4, and then the figure doesn't change. That is because in the hyperbolic world, you can't tie it like that. But I can increase the number of sides, like to 8, to 9. It will still work. I can also increase the number of vertices that to share to 4, to 5. Then you will generate different patterns. In the hyperbolic world, there is many ways to tie the plane. It's a bit okay. Go back to this is another work, also hyperbolic art of a person, of a mathematician. And how did they make it is they use what we call a straight line in the hyperbolic world. If you remember, sometimes ago I said a straight line does not look straight in some world. So in the hyperbolic world, straight line doesn't look straight. So straight line look like this, and people use all those lines. They interact it to get to an image like this. This is straight line in the world. Okay, next, I will talk about some dots or lines design. So some design that come from fonts or lines. There are quite a lot of them. Like this one. Starting from the dots, I will get some lines that makes you feel that this is still excellent. The technique used here is called chocolate salesman problem. Have you heard of this? Chocolate salesman problem. Have you heard of it before? Yeah, it is in the graph theory that the salesman wishes to travel into different city, but it doesn't wish to go for the same city twice, and then of course it also try to shorten the distance. So if you give me a graph, tell me the distance between the vertices, then I will there is some algorithm to find a path for the salesman. And here, how to generate the graph on the right is to first get the dot. So it means that if you get, well, if you get the figure of the sun, if you find somewhere that is darker, you put more dots there. If it is lighter, then you put less dots, like here, less dots. Then you consider all these dots as a city, and now you are a salesperson. You have to travel all these cities, and when you get to the darker part, that means when the dots are closer to others, then these cities are closer to others. That means it will encourage you to go from one city to another. And in terms of the path, there will be those paths there. And then like if some city they are further away, like this one and that one, they are further away, so the salesman will not go there. And so at the end, you will find all those gaps correspondingly. So that is from the dot to the line, use the popular salesman problem. There is another one. Okay. That is some word it is in the still life form. What does it mean? I somehow feel that these people are quite funny. These people just write the paper on how to generate all these numbers, all these figures. So there is a rules about the game of life. Living cells will die if they have too few neighbors because they are lonely. So like these cells, they only get one neighbor, it will die. This blue cell, it has 4 neighbors. If we get too many neighbors, it will also die due to the overpopulation. If there are some dead cells, 3 dead cells, around certain point, this point will alive due to reproduction. And then the last one is if there are only 3 neighbors, then these cells will remain alive, and then this pattern is stable because after this it never gets changed. Now, of course, we can use a mathematical model to check how the life will be like, which will be alive, which will be die, and then at the end there should be a stable form. These people they use the stable form to draw figures. So like all these dots, they are the alive form, and then it say that it is still alive form. It means that this form under the game of life, it will still alive, keep on alive. It will not die. You can also think that if you start with some other point, if you put the point somewhere else, then under the rules it will get changed, and then at the end it will end up a form like this. And you can use the form to generate any pattern that you like any letters or other kind of pattern that you like. And all this, it looks like just dark, black and white, but you can also add some color on that. And the color one is not a math part, but well, you can do that. These are in a still life form. The next part. Okay, I will speed up a little bit. It's on the magic sculptures, and of course, this will be big areas on people to work on. And there are different ways to make only sculpture. Like you can have identical piece of paper, and then just lock it. All these here, they purely interlock with the paper, no pulling, no tap, no glue. You can also do it with stakes, stakes that are identical, no tap, no gluing. Here I showed you some stakes, they are identical. I can take it from school. You can try to see that is my someone. I'm passing through this kind of stakes, and at the end it should end up something like this. And of course, we have some. There is some trick to generate all these kind of magic shape like this. Normally we will start with a polygon, like the one that I'm showing you. It has 6 sticks, so that is start with a cube, and then you just do some rotation on each side. Or each side you do the same though. So that means like here, start with a cube, and then you rotate each side of the cube in the same angle. Then you get different pattern, and once you combine them, you may figure out something more, and then well, if it interlock or whatever, then you just build on that. So everything starts with polygon and polyhedrons. The next one is fractals. Part is a little, it involves a little bit math, even though it may not look like. Fractals had some patterns that infinitely complex patterns that is self-similar. How to make that? Like this triangle. If you just look at one part, it is self-similar to the whole part. And then if you look at a small one, it's self-similar to the other. It occurs in the nature too, like if you find this piece of leaf, then you can repeat it, it is similar to the whole one. The puzzles have a lot of, if you like, you can check from the Google, there are a lot of them, and again, you may ask, hey, how does it relate to math? Even if it repeated, just keep on repeating. Now, puzzles is we can consider it as a area in complex dynamics. That means we consider the complex number instead of real number. We consider the complex number. Say here we get a very simple equation. This is just degree 2. One equation is enough to generate a famous cells. Let me show you the video. It looks like this, but when you enlarge it, you will see a lot of different patterns. One equation, I emphasize it. One equation in the complex plane will give you a pattern like this, and then now we keep on zooming and see all this. And yeah, they are all cells similar, and of course a little bit different. And then now you come back to the original pictures again. The map involved is a little bit different though, but it's still one equation. Let me stop here. So there are different parts. Once you enlarge it, you get this, and as you keep on enlarging it, you find different small features of the same edge. The next part is on tiling. I probably won't spend too much time on that, and because I know that we will have a talk next week on tiling. there are some types. This is the traditional one, and of course we may also wish to repeat the pattern. Here I just introduced one that is a little bit irregular, that is on the top. It comes from the Rodi diagram. In this diagram, we start with some dots that we call seed or site or generator. So those are these dots here. And then we will partition the whole display into different regions such that in the same color, each dot will be closest to this dot. So like this, and say if you look at these yellow regions, pick a dot, you check, okay, other states here, which one is closer to this red dot? It should be closer to this one. All these, any dot in this region should be closer to this state. You can also think that to generate this line, we just take a bisector between this, the perpendicular bisector of a line from here. Then you will generate this diagram. And sometimes people will say, hey, you often talk about it, and I don't know why we keep using the word. Is there any applications? If you look in Wikipedia, applications of this diagram, you will have a long list for you. But we talk about art today, so I just give you some artwork generated by that. So you get from some stage, you can get some colors. This is a variations. You can also use this kind of methods to generate letters. Like, okay, if you're in your mind, if you wish to print forms, then you get a shape first, and then you find out the location of the seed. You can also put some dots that represent your form, like your font, and then use those dots to define each cells. We can use it to hide some message, like this one. This is the same as that one, except I color the letters that is hidden, and here I have a message for you. Can you guess what is hidden here?
Happy Easter.
Happy Easter, thank you. That is a message for you. Happy Easter. You can generate your own one and do your own coloring, whatever you like, using this time. There are other artwork for something beautiful in math. They are the minimal surfaces or ratios. I don't have time to talk about all that. But if you are interested, we can discuss it later. And also the molecular multiplication. Okay. Still have some time. We still talk a little bit about the 3D printing experience that I have. I have produced quite a bit of stuff from the 3D printer in campus. You can print whatever you we can print a lot of things that you like this hands-on. It is a little bit flexible. You see that it moves. You just print it. You don't have to like assembly or do whatever. When it's printed, it looks like that. It can move. That is the dinosaur. Our printer is pretty good. Basically, if you get an equation, you can print. Like this one, it is a parametric equation. So you tell me the x coordinate, tell me the y coordinate, then you can print. You just ask computer print it. Of course, people like to print certain shape, like the half curve. This is the half curve. Have you learned about this parametric equation using the x and y? You just tell me what the x and y are. Then that will give you a curve in the plane, and it generates a curve. Have you heard of that? Should be. And once you get the hard curve, Well, you can do a little bit more. I have the animations is a bit. That is the Melville Street. Have you heard of Melville Street? Have you learned of it before? The Melville Street has no orientation service, and I can combine the Melville Street with the heart because we can get a equation coordinate for the Melville Street, and then we also know how to generate a heart shape. So at the end, you can get it Melville. Okay, that's for you. You just create your own. This one I can skip it. That is the design that I made. I like to make a projected plane. It is a design I did. If you attend my talk, my previous math talk, then you will know what it means. And then you can also choose some parts that you like. It will make it printed nicer. I think printing is quite addictive though. You know that I print so much. And yeah, I wish to advertise about my creative inquiry course. It is an undergraduate credit course. You will study with me in a seminar form, and then you can work on some topics that you like. Oh, it will be about art and math. You will get some research experience. I have presented probably more than 10 papers in this talk. You may not realize that sometimes when you feel that, this art is so boring, this doesn't look pretty. When you feel like that, it's likely that I'm actually presenting a research paper that you can present it in a conference or submit it to a journal. Those are not very difficult stuff, but you have to be creative. Just think about how to create this form, how to create this art. And if you get an idea, make it in practice. You can write a paper and go to conference, talk about it. If you are a graduate student or a postdoc, you can also join me unofficially or officially to the course. Just help me to run the course. Just if you are interested, let me know. And at the end, this is my last message to you. Get what it is now. This is my last message. And my last message is here. It is a paper in a way of folding. Originally, it looked like this. And the lines on it, it tells you how to fold the paper and then you get it in the correct orientation. After it fold, it doesn't work. When you fold it, I think it takes a lot of work if you really print it to fold it. But if you get stimulation, you can get it done. Thank you.
Questions?
So you were talking about the Mandelbrot set for a while.
Yes.
Did you know that those figures that you see when you zoom in, they have names? Like they have the Seahorse Valley and the elephants and all that stuff.
Yeah, I'm very curious to my creative inquiry course so that you can let our students know about it.
So yeah, there's also the Julia sets. Like
Yes.
you were showing the Mandelbrot set.
Yes.
Julia's set, right?
Yes, yes.
So what is like so the Mandelbrot, you have that formula, z squared plus c. And if you continually iterate, the points in the Mandelbrot set are the ones that do not diverge to infinity.
Mhm.
What is the definition for the Julia sets? I was trying to remember it.
I think you swap the role of C and Z. C and Z. One you can change the C, one you can change the Z. I can tell you one. Yeah, he asked about the Julia sets. I actually find some lines about the Julia set, and because he mentioned it, so I'm sure. Otherwise,
The projector went down by the way. Oh, no, that's all right. There.
Julia set. And also from one equation in the complex way. And people also make some fun with different periods and different levels, and then they play with it to get it fun.
Other questions?
When you talked about like the music and the integers like the invisibility, do you see like a lot of different like mathematical patterns within music like today? Something like that, or like with different melodies, etc. Or is it just
You can create your own thing. You know, the author also mentioned like because she liked the divisor pause, look at the pattern, and then at the end she created those music. That website was produced by her, and then code people on it.
You ever thought about? I mean, could you do something similar by looking at the decimal expansion and using that to like make music? Right, because if it's a rational number, it will repeat.
Yeah.
If it's irrational, it'll not repeat.
People have actually done that with pi.
Right.
They just, I think they did the pi expansion in base 8 and then identified the digits with notes from 1 to 8. And then just like.
See.
Yeah.
Actually, I think in hexadecimal, so if you look at the digits of pi, which is a transcendental number, right? Most anything that you would do to get, if you want the 100th digit of pi, the amount of work you have to do, basically, you have to compute all the previous digits, right? But there's actually a closed form way to do it in hexadecimal, right, in that base, right? So it has to do with these various infinite, it's a number theory thing, but there's a way where without computing the previous digits in hexadecimal, you can figure out like the millionth digit of pi, which is kind of bizarre. So it's a late pi day thing, I guess. Other questions? All right, let's thank our speaker again. Anybody out there, any questions? Well, I'm gonna stop sharing for a minute so I can see what's going on. No, just applaud. Okay, folks, I don't think there's gonna be a math club next week because we've got the undergraduate awards day on this day, and we don't want to take away from that, but I'll keep you posted. Other than that, y'all stay warm, good weekend, and we'll see you in 2.